Okay, so my name is Randy MacLeod. I work at Wind River Systems on Wind River Linux, and I'm going to tell you about Rust and merging Metarust into OE core. So overview of the talk is, as I said, to talk about Rust and the Metarust layer and the work of merging it into OE core and why we want to do that. And then once we actually get there, what'll come next. So I'm assuming that people don't know much about Rust or Metarust, so this is a very quick talk, so I don't have, it will be a full language tutorial or things like that. It's very much an overview. So Rust is a memory safe and concurrency safe, performance-oriented systems language, much like C or C++. It doesn't have a garbage collector or things like that, so it's suitable for implementing operating systems or performance critical deterministic software. And it goes back a while, started in around 2006, as I mentioned on the slides. It was adopted by the Mozilla Foundation in 2010, and they had a 1.0 release, which guaranteed backwards compatibility back in 2015. So it's, in the language world, it's probably a little newer than Go, but same generation. For several years now, it's been a very popular language and winning the Stack Overflow annual survey of developers' favorite languages because of the properties that it advocates and tries to deliver to developers. So the idea is performance, control over memory safety, and fearless concurrency, and a really good community. There's been several Rust conferences over the years, and portability as well is achievable and fairly easy, but of course you can write platform-specific code as well. So I mentioned the performance. I haven't looked at the language shootout website, that it's similar to C and C++. The memory safety is the default. You can write memory safe code in C++ if you're very disciplined, and many people achieve that, but people are fallible, and by default, Rust is safe. Rust will let you write unsafe code if you use the unsafe keyword, and even in that case, the compiler will insist on certain workflows so that it doesn't give you complete freedom. Whereas in C and C++, you're free to shoot yourself in the foot, as they say. So because of this memory safety and the type checking and the language design, many concurrency errors are also caught at compile time. And so the cost of this memory safety and concurrency freedom is slightly longer compile times, which I see as being a replacement for running the compiler and running Valgrind and running other tools that come along with the C and C++ environments. Rust isn't just a compiler, it's also a collection of tools and a community. So Cargo is the build tool. They try to have very clear docs and helpful error messages, which is similar to the GCC versus Clang advocacy. So let's start with a simple program when you're compiling manually. To get started on your workstation, Ubuntu or Debian or Fedora, whatever you like to use, you can either use the system package manager these days, I think, but most people, especially if you got started a few years ago, use this horrible script to install from the web. So you can look at the rustup.rs website and follow their directions. Once you've done that and you log back in again, you can type in a hello Rust file and then just invoke Rust in a very much analogous way to using GCC or Clang. And when you look at that output of the compilation, you'll see that you depend on the 4 shared libraries that I list there. This shows you that even though it's a simple program, Rust has these 4 dependencies. So it's prepared for multi-threading, it's a libp thread, and it has libc, libdl, and libgcc. The size by default is fairly big, about 280K. But it's with a bit of work and some options, you can strip it down to 6K. So it's clearly similar to C and suitable for embedded systems. So as you scale up to larger and larger projects, you'll see that Rust is statically linked, and I'll probably talk about that in a future slide. The more normal way to use Rust is to use the cargo package manager. And so you'll start with the cargo new to create a new project. You can either create a binary or a library. The default is a binary, so create a hello cargo project and cd into that directory, and you'll find that you've already got a very stubbed main created for you. So then you can just type cargo build, and that'll generate your binary. You run cargo run to run the binary. Cargo test, so the development environment is set up for industrial software approaches. So tests are integrated into the language and into the package manager tool. You can also do, Cargo also knows about a repository for packages on the web called cargo.io. And so you can use the command line tool to search for something like Tipsy, which is a network protocol that I worked on 10 years ago. It's fairly obscure. So I searched for that the other week, and surprise, surprise, someone has written bindings for the Tipsy network stack in Rust. And that sort of gives you an indication of the scale of the development community and how many packages are available. I think there are roughly 50,000 packages. So, it's not small, but it isn't sort of the millions that you see for software on GitHub in every language imaginable. So let's say you assume you don't want to install Tipsy. Let's look at a developer tool. So you can run cargo install ripgrep, and I'm just going to walk you through what that does. Ripgrep is a faster implementation of grep written in Rust. You can also read it as rest in peace grep, because there's no longer a need to use grep, perhaps. So the first thing on the second line here is that it updates your cargo.io index, and then it downloads the main ripgrep program and all of its dependencies, which in this case are 14 crates. A crate is essentially a library in the C and C+ world. And then it compiles everything in the order required, so it handles the dependencies, much like bit-big recipes do. And then tells you that it's finished and installs it in your home directory, which is in your path by default. And then you can run ripgrep or RG, and you'll get slightly better performance and slightly different usability than grep, but it's a nice tool. So that's fine. You just might say, well, why does Yocto need Rust? And the bottom line is that the more and more software is being implemented in the language, so it's time to merge it into OE core. There'll be pros and cons, of course. We've already suffered from not having Rust because several packages, specifically librcg, have been held back a few versions because we don't have the toolchain in OE core. So I mentioned the other 2 points, the pros of using Rust. The cost will be that there'll be another tool chain to support, and we'll have to develop the expertise. And myself and some of my coworkers at Windover are going to be able to do some of that, but of course we'll need a community to pitch in as well. I've mentioned the downsides, the Rust build times. I don't have actual numbers, but there can be like a factor of 2 or 3 longer build times than C or C++ application of similar scale. But as I mentioned, this is the cost of safety. The compiler is doing lots of checking. is also doing static linking by default. So if you have two Rust applications and they share all of their libraries, the two applications will duplicate the text code instructions for each of the libraries, unlike having shared libraries in C and C++. This is, it's possible to avoid that in Rust, but it's not all that common. So one solution to that people have used for a replacement for core utils is much like BusyBox produces a single executable and produces a series of links to that. You can take the same approach. And I think I was one of the people who started on the Metarust layer did the same thing in their application at Lexmark, a printer company that has been using Rust now for a few years. So we don't want to just run cargo Rust code on our personal workstations or work workstations. We want to do cross-compilation and embedded systems development. One way to do that using Rust, because to do this statically linked, is to just install the GCC cross tool. So I'm doing this on Ubuntu. So I install the AArch64 toolchain, and then I add that as a target in using the Rust up tool. And if I modify my cargo config to specify for the AArch64 target, I'm going to use the linker given, then I can just call cargo and say build for this AArch64 target, and it'll happily cross-compile. So cargo and Rust specifically, because they're based on LLVM, already have the ability to generate code for a variety of targets. And so this is fine. It's very convenient for developers, I think. You just build on your own workstation, you produce a Arch64 target binary, you copy it over to your system, and you can run it. But of course, if you're doing production environment, you want to be guaranteed that the exact versions of both Rust and your linker and your C library and so on all match up. So we probably want to teach cargo how to do that by using the Yocto SDK C and C++ toolchains, or just put cargo and Rust C in our SDK. And that's something that I haven't done yet. I'm not aware of anyone who has. So let me know if you know more about that. What is the Metarust layer? It's a Yocto-compatible layer, as you might expect. It produces the Rust C and the cargo cross tools. It was started about 6 years ago by the people I list here. So there's about 35 people who have contributed to Rust C. I'm not one of them, so I'm really just trying to move things over to OE core. It was more active in the early days with several hundred commits a year, but recently it's more like 40 commits a year. And the major activity is keeping up with the Rust community. Unlike a lot of toolchain development cycles that are sort of an annual or or less frequent uprev cycle, Rust releases a new version every 6 weeks, and it does have longer term, sort of long-term support milestones. I think they call them additions. So we need to come up with a strategy about maybe supporting the 2018 edition, I think it's called, or optionally using the bleeding edge latest official release. So if you look at the what's in the Metarust layer, it's a typical stage 1, stage 2 toolchain build and a sample Hello Rust application. And if you look at use the PY boot chart task to what I did, I believe was I built core image minimal, and then I just added the Rust Hello World application. And of course that needs to build the toolchain. And so you can see if you squint really hard, you can see the different stages of the build.
And I have the full PY chart. This is a summary, of course. The take-home message in this slide is that this is building Rust native, and it is really quite slow. It takes, I think it's roughly 10 minutes on a fairly hefty 192 core build system that I have at hand. And anyway, so it works, and then end up producing the hello Rust and adding it to core image minimal. So we'll want to fix that CPU bottleneck, but we just haven't gotten there yet. So you have this wealth of bitbake recipes on crates.io, as well as other things that are not necessarily published to the community, but you can find on GitHub, or you have within your on your file system as your own project or your work Rust project. And so there's a tool written called Cargo Bitbake. It's on GitHub. And so it's also on the crates.io website. You can just use Cargo on your workstation to install Cargo Bitbake. And then you go to, say, for example, the ripgrep source repo that you've cloned from GitHub, and you type Cargo Bitbake, and it'll produce a Bitbake recipe. And the contents of the recipe include everything you need to be able to compile it using Metarust. And so the end result is you can get Bitbake ripgrep and install it into your image. So that's fine. That works in Metarust, and so now we need to move things over. It shouldn't be a big deal, but you never know. I've been sort of working on this off and on for probably far too long, but moving things over from one layer to another is fairly easy. I've done that. You add a couple of recipes that depend that Rust needs, and move them over from Meta OE. That's also fairly easy. And then try upgrading librSVG to, I think, the 2.5 branch. And librSVG is a GNOME project, and GNOME has really started switching over to Rust, but they also need to deal with backwards compatibility. So librSVG, which is used to be written in C, has a C API, but the developers are trying to maintain that API, but provide the core functionality of the code in Rust. And so I'm not sure if this is done yet. I have something that builds, but I haven't linked applications against it, so I suspect that there is still a problem. There are two ways that librSVG can be built. One is using AutoTools, and one is using Cargo. So currently the Cargo approach works, and the AutoTools doesn't. The bottom line in the AutoTools build is that you try to get the part of the build asks rustc to print its configuration, for example, and it just can't find the configuration. So it looks to me like it's a configuration issue, because the stage 1 and stage 2 versions of the compiler are fine. And I started debugging that, but I haven't resolved the problem yet. So I'd also like to thank Adrian Bunk for this Cargo disabled bitbake vendoring, which enables the Cargo build to work. So I went on after that and tried to look at what else needs to be done. And GStreamer and probably other OE core packages depend on librSVG. I also did a bitbake world, and there are a few problems with that as well, including the fact that for some reason I can't exclude rustc and Cargo from the target build. So that's probably a trivial thing, but that's where things are at the moment. And the reason I wanted to exclude them is that that's one of the limitations of the Metarust code, is that you cannot build Cargo and rustc for the target yet. So I'm almost done. I haven't heard anything. I hope that things are in good shape here. Let me continue. So there's another problem with the current state is that RISC-64 isn't supported in the version of LLVM that we have. There is an update of LLVM to 11, and it's possible that this will be fixed. So we'll need to bring that into OE Core, hopefully in the next few weeks. We also need to be able to support building Yocto and OE Core on ARM64 build systems, and that may be possible. I just haven't tested it yet. RustUp does work on my Raspberry Pi 64-bit Raspbian distro, so it's possible. It looks like it shouldn't be a problem, but we'll have to see. So I mentioned the other 2 points, so I'll skip over those. And so what's next? This plan, as usual, is to get it merged, do something else, and then profit. So we'll see how that goes. We'll need to continue to track the Rust upstream 6-week release cadence. Currently, we have Rust has its own copy of LLVM. There's not a huge difference, but it's not a trivial difference either. So we need to try to unify those 2 repos because they're fairly large, and it's not really a great idea in terms of software footprint to have these duplicates. It'd be nice to get the Rust cargo environment cross-compiling to build on the target. I don't think that's necessary for merging, but we'll have to wait and see what people think. And the dynamic linking would also be nice, but again, that's sort of a longer-term requirement, I think. There has been discussion in the Linux community environment about doing driver development in Rust, taking advantage of its safe nature. And I don't think there's any plan for that. If anyone knows, if I expect that'll be a year or 2 down the road, so it won't affect the spring release of the Yocto. So if anyone knows more about that, please let me know. And I'm sure there are many other things that I don't know about, so I welcome input and anyone's ideas about what else we would need to do. So thank you for your time, and I